Hey guys, so this video is going to be about time dilation. Special relativity is the next topic in the class, and time dilation is a big part of it. I wanted to make this video because people think of special relativity and time dilation as really being very science fiction-y, as different times and different reference frames, people growing older, people getting younger. What does this stuff all mean? It's not science fiction. It's a very well-regarded fact, which comes only from the postulate of Einstein's, which says the speed of light is constant in all reference frames, in all inertial reference frames. So I want to show you how that comes out, how that works, using just that postulate and some very simple geometry. This really changed the view of space-time and how everything works, and that view of space-time has been shown to be true in every single situation. It's one of the most well-tested theories in physics, and so this is the basic application of that, and so I really want you to convince yourself that there's nothing crazy going on here. We're not going to be able to apply this to black holes, we're not going to be studying any crazy gravitational systems, but this is the basics of Einstein's theory, which really revolutionized how we think about physics. And so I want to convince you that it's not a crazy thing. Okay, so now let's get to it.
So there are two postulates of relativity, and it's through only these two postulates that we get all the interesting behavior that we're going to study for the next week or so. So the first postulate is that the laws of nature are the same in all inertial reference frames, inertial meaning non-accelerating. So this is significant because when you do Galilean transformations, which are non-relativistic transformations, the laws of mechanics are the same in all inertial reference frames, but the laws of E&M are not. So E&M changes in different inertial reference frames. So Einstein started with the postulate, saying that shouldn't be true. The laws of nature should always be the same in all inertial reference frames. That's one of his starting points. So he was constructing a theory of physics which was more complete than what had come before he got on the scene. The second postulate is that the speed of light is constant in all these frames. And I should say that I mean the speed of light in a vacuum. The speed of light through materials actually is different. If you shine the light through water, the speed of light through the water is actually different. So what I'm talking about is the speed of light in a vacuum, through space. So this is actually kind of a very crazy idea that the speed of light is constant in all these frames. So imagine if this was true for something normal, like say the speed of a baseball when you throw it is the same in all of these reference frames. So let's put me in a car traveling with a velocity of 50 miles an hour, and then I throw my baseball, and let's say that I throw the baseball at also 50 miles an hour. I might be able to do that. So if I did that, I would be moving at 50 miles an hour, I would throw the baseball at 50 miles an hour. I would see the baseball moving at 50 miles an hour because I'm moving with the car. So relative to the car, it's pretty obvious the baseball is moving 50 miles an hour. But if there's somebody over here, say standing on a hill, which is not moving with the car, they are stationary relative to the car, if baseballs acted like the speed of light, they would see the baseball moving also at 50 miles an hour. So think about that. That's kind of crazy. That's not how we would observe this happening. This person in real life, in our real life, would see the baseball moving at 100 miles an hour because it would add up 50 and 50 and get 100. But if baseballs obeyed the relativity postulate, then this person would also see the baseball moving at 50 miles an hour. What would they see the car doing in that case? Would the baseball be stationary relative to the car because both things were moving at 50 miles an hour? So this is the postulate that Einstein used for the speed of light, which is a little bit crazy. It sounds a little bit crazy, but it's this identification that the speed of light is a unique thing in the universe that allows us to do relativity. Okay, so let's move on to the actual example. Okay, so this is figure 9.5 in your textbook. This is on page 278. And we have one person on a train. Here's the train. Here's the person on the train with a flashlight. She's going to shine the flashlight up. It's going to bounce off a mirror and return to her. This person is outside the train observing this process. And so the question is, what effects to the postulate of the speed of light being constant do we expect to observe? Does this mean anything? I mean, like the baseball example, we should expect this to mean something pretty significant. We will want to say, what does this really mean? So first question is, how long does it take the beam of light, to go from up to the mirror and back? What's the total time of travel for the light? Well, that's pretty simple. It goes a distance of 2d. Speed of light is c, so the time it takes is just 2d divided by c. So I've called this delta tp. That stands for proper time. We'll talk more about what that means in class. Don't worry about it. But for the moment, I want to see the effect of assuming that the speed of light is constant. So I don't want to say c, I don't want to assume it's constant. I want to put a tag on that to mean that I mean the speed of light in the moving frame. So I'm going to put a t on that. So that means the speed of light in the train. Okay, so now what does the person outside the train see? He sees the beam of light not make a straight path like that, but because the train is moving, he sees the beam of light make a triangle. Okay, so that's the path of the light. So this is a triangle. The edges of the triangle should obey Pythagorean Theorem. So let's do the Pythagorean Theorem on this triangle right here. The total distance the light travels in the frame of the observer outside the train is v delta t. Half that is v delta t divided by 2. So applying Pythagorean Theorem to that shaded in triangle, we get the following. Okay, so here's the application of the Pythagorean Theorem. I also want to tag that speed of light as being different from the one that's in the train, so I'm going to put an O for outside the train there. So this distance right here, we can measure this in two different ways. One from outside the train, which is what we do here, but also this distance is the same as inside the train right here. So let's solve for d here and plug it in. Okay, there we go. So now we have two different times. We have the time outside the train and the time inside the train. So let's try to relate those two to see how they're connected. So this is just going to be some algebraic manipulations. I'm just going to breeze right through it. You can be more careful and do it yourself if you like, or you can just trust that I'm doing the right thing. And so at this point, we notice that there is this factor here, which is the speed of light outside the train divided by the speed of light inside the train. Well, I started with the idea that maybe the speeds of light are different, are not related in any way. Einstein said, no, actually, these have to be the same all the time. So now what I'm going to do is I'm going to call that c, call this c, call this c. This thing becomes a 1. I'm going to take the square root and get the final result. Okay, so the relationship between the two times is given by this ratio, 1 over the square root of 1 minus v over c, right here. So this came about because I assumed that these two speeds were equal, but the only other thing I used was geometry. I said speed of light is moving some distance here, it moves some distance in the outside reference frame. Those are the only tools I used, no craziness. And I got this basic result showing that the elapsed time in the two reference frames were different. So we're going to explore some of the consequences of this time dilation equation in class, but the real takeaway from this is I don't expect you to be able to derive this in class. I don't expect you to be able to do this in an exam. I expect you to be able to use this result, but not necessarily rederive it. But you need to understand that the basic idea here is you start with the idea that the speed of light is constant in every reference frame. So starting with just that and some thought, you end up with the idea, the rather dramatic and groundbreaking idea that the time differences can be different in two different reference frames. This woman who's traveling along on this train, if she gets off the train, compares her age to this man, her age will be less. She will have aged less than that man. And the only thing you're using, speed of light and some thought. This is where Einstein's genius really comes from, is being able to understand that just a basic postulate like this could lead to such revolutionary changes in how we think about physics. Okay. I'm done. Enough going on about this. I hope that we'll be able to understand this better in class and do some examples to give you a sense of how this works. Okay, thank you guys.